Have you ever just stopped and wondered how your phone knows what to do? You tap an icon and an app opens. You swipe and the screen scrolls. It feels like magic, doesn't it? But behind every single one of those actions, there's a language of pure, cold logic. Today, we're going to pull back that curtain and see how computers really think. And here's the wild part. You might already be speaking their language and not even know it. So let me ask you something. Think about the last time you were in the kitchen, right? Maybe you were baking a cake, trying out some new dish. You had a recipe in front of you, a list of ingredients, a very specific set of steps to follow. Preheat the oven to exactly 350 degrees, then mix the flour and sugar, then add the eggs. Well, believe it or not, that recipe, that's an algorithm. Yep. At its core, that's all an algorithm is, a precise set of instructions made to solve a problem. In this case, the problem is, I'm hungry and I want cake. And this exact same idea, this step-by-step logic, is what powers every single app, every game, every website you've ever used. So let's start breaking this down. All right, so section 1, thinking in recipes. We're going to stick with this analogy because it's just so perfect. A good computer program, just like a good recipe, needs structure. It's all about taking a big, complicated goal and smashing it down into tiny, clear, manageable steps that get you a result you can count on every single time. So let's get this definition locked in. An algorithm is a precise, step-by-step set of instructions designed to perform a task or solve a problem. Now, the key word here, the one that matters most, is precise. You see, you can't be vague with a computer. You can't just say, add a pinch of salt. The computer's going to go, what's a pinch? It needs an exact instruction. Add exactly 2.1 grams of salt. Every step has to be crystal clear, leading perfectly to the next, all the way until the job is done. Now, you can't start cooking without your ingredients. It's the same in programming. And in the programming world, our ingredients are data. So let's take a look at the basic building blocks that every algorithm needs to work with. First up, we've got data types. You can just think of these as your ingredient categories. Are we working with liquids, solids, spices? For computers, it's things like numbers, like 350 degrees, or text, which programmers call strings, like the name of your recipe, awesome chocolate cake. And then there are simple true or false values called booleans. Think of it like a light switch. Is the oven preheated? Yes or no, true or false. That's it. Okay, so we need a place to put these ingredients. That's where a variable comes in. Imagine you have a measuring cup, and you put a sticky note on it that says sugar. The amount of sugar in that cup might change, right? Maybe you double the recipe. A variable is just like that. It's a named container in the computer's memory that holds a piece of information that can change while the program is running. But then you've got the opposite. Some things are just set in stone. We call those constants. Think about it. There are always 12 eggs in a dozen. There are always 60 minutes in an hour. In our recipe, that baking temperature of 350 degrees, that's a constant. It's not going to change. So that's the big difference you've got to remember. Variables can be updated, but constants, they're fixed. Okay, so we've got our data. Our ingredients are all set. Now it's time for the actual instructions. And this is where algorithms get their real power. Because they aren't just a straight line of steps. They can make choices, and they can repeat actions, and that's what allows them to handle pretty much any situation you throw at them. This right here is a decision. Programmers call it an if-then-else statement, but really, it's just a fork in the road. The algorithm checks a condition, a simple true or false question. Is the cake golden brown? If the answer is true, it follows one path. Take the cake out of the oven. If the answer is false, it follows a totally different path. Bake it for 5 more minutes. This branching logic is absolutely fundamental to how programs react and adapt. And these questions can get more complicated. A simple condition is just one question. Is it raining? Easy enough. But often, a program needs to check a few things at once. That's a compound condition. It's where you use words like and or. For example, is it raining and is it cold outside? See, now both of those things have to be true before you decide to grab your heavy-duty raincoat. Algorithms use these complex checks all the time to handle more nuanced decisions. But what about when you have to do something over and over and over again? Well, that's what a repetition structure or a loop is for. I mean, imagine you have to crack a dozen eggs. You're not going to write crack an egg 12 times in your recipe. That would be insane. Instead, you just create a loop. You say, as long as there are more eggs in the carton, repeat these steps. Grab egg, crack egg, whisk egg. This is the very heart of what makes computers so fast and efficient. It lets them do thousands, even millions of things in the blink of an eye. The only real danger is creating an infinite loop, which is basically the computer equivalent of getting stuck stirring the batter forever. So, we've been handling our ingredients one by one, but what happens when you have a whole pantry full of them? To build really powerful algorithms, we need smart ways to organize huge amounts of data. Let's start with a simple shopping list: flour, sugar, eggs, milk. It's just a single, ordered list of things. In programming, this is called a vector, or more commonly, an array. It's a way to group related items together in a sequence. Each item gets a number, an index, so the computer knows where to find it. So flour is at index 0, sugar is at 1, and so on. Yeah, computers like to start counting from 0, it's a whole thing. But this makes it super easy for an algorithm to zip through the list to say, check if you forgot something. But hey, not all data fits neatly into a single line. What if your data has rows and columns, like a calendar or a bingo card? For that, we use a matrix. A matrix is just a grid, a table. You can even think of it as a list of lists. This two-dimensional structure is incredibly powerful. It's used for everything from the spreadsheets you use at work to the game board in your favorite strategy game, all the way down to the grid of pixels that are literally forming the image you're looking at on your screen right now. So we've looked at the ingredients, the instructions, the organization, but here's the thing. Learning about algorithms is about so much more than just telling a computer what to do. It's about developing a really powerful new way to think, a new way to solve problems in pretty much every part of your life. So what does it really mean to think this way? Well, it's about building a certain mindset. It starts with valuing innovation, always asking, is there a better, faster, more efficient recipe for this? It means you have to embrace research to really understand the problem you're trying to solve before you even start. And maybe most important of all, it means you have to think critically. You have to look at the way things are done and constantly ask, can we make this better? Is there a smarter way to get this done? And honestly, this is the biggest takeaway of all. We started this whole journey with a simple recipe for a cake, but this way of thinking, it goes so far beyond the kitchen or computer screen. Algorithmic thinking is a universal problem-solving skill. It's about taking any huge, complex challenge, planning a big project, organizing a vacation, even tackling a personal goal, and breaking it down into a clear, structured sequence of logical, manageable steps. So I'm going to leave you with a question to chew on. Think about your daily life, your morning routine to make coffee, the way you sort through your email, the steps you take to get ready for work. What's one of those routines that you could break down into a precise, step-by-step algorithm? Give it a try, because once you start seeing the world this way, you'll start finding recipes for success absolutely everywhere.